Okay, guys, we are going to explore some of the different types of equilibrium calculations. There's actually six of them, but we're going to only focus on four for this week, and we'll just do one other one the following week, which is a little bit more complex. Anyways, what's going to happen is you are going to be given an equilibrium equation. And in terms of this worksheet, if you don't have the capability of printing it off, that's okay too. If what you can do is on a separate line piece of paper, do the following examples with me so you have reference to it. And I noticed that the equilibrium arrow is missing from this particular reaction. So what this means is when you see that double arrow, we have a reaction that proceeds in the forward direction. So these collide to make some of the products. And in this scenario, the products will re-collide and form reactants. And again, that happens within a closed system. We always consider the right of the arrow our products and the left of our arrow the reactants, just so we have starting point. Whenever we say that the reaction proceeds to the right, we mean going towards the products. And when we say the reaction proceeds to the left, we mean moving back towards the reactant side. Okay, so they're telling us at this temperature, you are given the following concentrations at equilibrium. Okay, so at equilibrium, the concentrations are found to be 0.24 moles per liter. Remember, the capital M just is short form for moles per liter. And we have the same given for CO2, 1.8. Water is 0.88, and same with carbon monoxide. They want you to calculate the equilibrium constant. The first thing that you want to do is you want to make sure that your equation is balanced. So you've got 2H2, 2H2, one carbon, 2 oxygens, 2 oxygens. Perfect. Next thing you want to do is set up your mass action expression. So you can either write Kc or Keq. You would have seen this in the last module, type 1 and type 2 type calculations, but we're just revisiting it again here today. So what you want to do is you want to write your mass action expression, products over reactant. So what I do is I take the concentration of water raised to its exponent, which happens to be a 1, times the concentration of the other product, all divided by the reactant concentrations multiplied by each other. Okay, and again, all of them have coefficients of 1, so their exponents are 1. All you need to do now is sub in the values for your concentrations. Okay, and as I do that, and I multiply this one by, which one is that one? 1.8. Okay, there we go. And when we plug that in on our calculator, we get a value of 1.7925 repeated, okay, 25925 and so forth. So what we're going to do is, again, we probably should keep it to 2 sig fig, so our answer would be 1.8. There are no units for equilibrium constant, okay, so no units at all. Okay, it's just a constant. It's really just a ratio between the products and the reactants. Now, what does that value tell us? Well, previously you would have learned that if your KEQ value is a lot greater than 1, okay, then we say that at equilibrium, the product concentrations are favored. So there's more product than there is reactant. If you have a lot less than 1, we would say that it is reactant favored, meaning that there's a lot more reactant compared to product at equilibrium. If you have a KEQ value equal to 1, then we would say that you have equal concentrations of products and reactants. In this case, this is pretty close to 1. However, we would say it slightly favors product formation. So there's a little bit more product compared to reactant in the container at equilibrium. Let's take a look at calculation number 2. So calculation number 2 enables us to calculate an equilibrium concentration, and we are given the equilibrium constant and some of the other equilibrium concentrations involved. So again, we want to make sure that we've got that double arrow in there. We've got methane plus water yielding carbon monoxide and hydrogen. So we want to just make sure that that's balanced. One carbon, 6 hydrogens, 6, and we've got 1 oxygen. Perfect. Then what we want to do is we want to automatically set up a mass action expression. So we have our KEQ value is equal to our products. Now notice that H2 has an exponent of 3 because of that coefficient all over your reactants. Okay, and then what I do is I take a look at what is given. So I'm given the concentration of carbon monoxide, I'm given the concentration of H2, of methane, and they're wanting you to find the concentration of water. So this is the one that we do not know. We're also given the KEQ value. So what I do before I plug anything in, I want to rearrange this expression to isolate and get water by itself. And in order to solve for this as a variable, if you were in math, this would be sort of like your x value, you have to bring it to the top as a numerator. So what I do is I would take this and I would move it to the other side of the equal sign. And so water would be moved up to here. So you would have water up here multiplied by KEQ gives you all of this. But what I can do then is move KEQ to the other side, and what I would be doing, so originally, this is what I had, okay, I would just sort of rewrite out, okay, just to show you, and I want to get KEQ to the other side because it's being multiplied here. When you bring it to this side, it would be divided, okay? So now I can start to substitute in what I do know. So I'm going to just write that. Okay. Plug in all of your values, and then that way you've got water's concentration, what you're solving for. So plug in the concentration for carbon monoxide, plug it in for your hydrogen, remembering your bed mass rules, you have to apply that exponent first. You're going to divide that by the concentration of methane multiplied by the KEQ. Oops, I shouldn't put it in square brackets because it's not a concentration. Okay, so then let's take a look at what that would yield. So on the top, what you have got is 0.1536. And on the bottom, when I multiply that out, you get 2.268. And my final concentration, when I plug that into my calculator, that yields 0.06. Now take a look on my calculator. I get 7724867. What I want to do is I want to take a look at my sig fig in the original questions, and it looks like I have 1 sig fig. So if this is what I had, then this would be 0.07 moles per liter, or capital M. So that would be the concentration when we are at equilibrium of water.